Hey guys, I'm Diana Soltani. I'm a junior at Rutgers. Last semester I took Grad AI. It was a really interesting course, learned a lot of cool things. One of the cool things that I learned was neural networks, and I thought it was so cool that I wanted to bring it to you guys here today. If you want to follow along or code along at the end, you can go on tinyurl.com to Hacker Hour, and this will take you to the GitHub repo where there's the link to the slides. There's the finished code of a perceptron network, which is the one we'll be coding today, and the code template. And I'll go over what a perceptron network is, don't worry. We'll code it together. I suggest you open up the template before the perceptron, just so it's more of a learning experience. So how many of you are freshmen? Raise your hand. Interesting. I tried to cater this as much to you guys as possible, even though it's like a grad level topic, but I really hope you guys understand at least like 30% or 50%. But it's really interesting. So as long as you take something from this lecture, then you'll be fine going into like grad AI or regular AI or any AI. Anyways, so I'm going to start with the types of learning we have with neural networks before I go straight into the definition of neural networks itself. We have two types of learning, supervised learning and unsupervised learning. When we have supervised learning, we want the supervisor as a teacher when learning. So we can think of supervised learning as learning in which we teach or train the machine using the data which is well labeled. That means that some data is already tagged with the correct answer. We can do this with spam filters today, for example. You have a model, right? And you have a set of emails that are marked as spam, which are actually spam, and you have a set of emails that is marked as not spam. And you would train your model on this data to test with live data. And I'll go more over this later. So unsupervised learning is the training of a machine using information that is neither classified nor labeled. And this allows the algorithm to act on that information without guidance. So some of the algorithms are clustering and association. And a clustering problem is where you want to discover the inherent groupings in the data, such as grouping customers by purchasing behavior. Association is kind of a learning problem where you want to discover rules that describe portions of your data, such as some example when you have people that buy X also buy Y. An example of unsupervised learning is Dota bots. How many of you guys have ever played a MOBA, like Dota or League of Legends? All right, not a lot, but it's okay. These games, these MOBAs are like these 5v5s where you have 5 people trying to attack another team's tower and vice versa. So it's a 5 versus 5 player game. And if you guys have played these games, you've probably heard of the OpenAI 5, which is the name of a machine learning project that performs as a team of video game bots, team of 5, playing against human players in the video game Dota 2. And these bots don't learn immediately from the first game. It takes them a couple of games by understanding other users' behavior. So if a team attacks turrets, then the bots learn to also attack turrets. If a team does ganks, which is just attacking from unexpected positions, the bots will also learn how to do the same thing. These bots have, just like the chess bot that we all famously know, has beaten the best team in Dota, just as a cool, if you want to know. So what is actually a neural network? I haven't really gone over that quite yet. Let's just try and recall some biology. We all know what neurons are, right? It's the cells mostly in your brain, and we take signals from dendrites, and they move through the axons, in which the outgoing signal may then be used as another input for other neurons. So, as a loose definition, neural networks are a set of algorithms that are loosely modeled after the human brain. These algorithms are set to recognize patterns by interpreting some form of data, and that can be understood by the computer. So this is what a neural network actually looks like when you think of it in terms of code. You have a set of inputs, right? And then you have a couple of hidden layers and an output. And each hidden layer has 2 nodes. It could have 5 nodes. It really depends on the developer and how you model your neural network. So usually a vector of features will be fed into your neural network. And then a hidden or a set of hidden layers takes a set of weighted inputs to produce an output through an activation function. If this is a lot to take in right now, it is. I'll go over it soon, but we'll see this more in detail. So some of the essential components behind a neural network is the learning rate, the activation function, regularization, and regularization rate. So the learning rate is a tuning parameter when training a neural network. It affects how quickly our model can converge to a local minima. And a local minima just means the best accuracy. What's the most accurate conclusion our model can arrive to? We want to model to arrive at the best accuracy at a reasonable pace, though. In research and industry, a famous quote is, less training time means lesser money spent on GPU cloud computations. So basically, if we set our learning rate to a higher value, our model will may converge to a value much faster, but it may also overfit your data. And I'll go over that soon. So you want to choose a reasonable learning rate. So an activation function. This gives the output of a node given an input or a set of inputs. In artificial neural networks, the activation function of a node defines the output of that node given an input or a set of inputs. A standard computer chip circuit, for example, can be seen as a digital network of activation functions that can be on or off, depending on the input. We'll see an activation function when working on our own neural network soon. So as for regularization and regularization rate, these are just techniques used to reduce an error or minimize the growth of the weights to some unreasonable size. So this is done by fitting a function appropriately on the given training data set, and this is to avoid overfitting. Large weights in a neural network are a sign of more complex networks that have overfit the training data. And we'll go over what overfitting is in detail soon. Penalizing a network based on the size of the network weights during training can also reduce overfitting. So we have different types of, data. You have testing data, training data, and your live model. To start, your live model will probably be when your product is live, what people are actually putting in as data, how the people interact with whatever product you applied a machine learning algorithm to. Your training data and your testing data actually come from the same data set. So we can actually, let's see. Is it okay if I move this up? Yeah? Okay, cool. Whoops, my bad. So this is your main data set. Everyone can see this, right? It's clear enough. You can essentially randomly split up your data sets. So this is a subset, this is another subset. These are all subsets, right? And your training data will actually be one of these subsets, for example. I'll say, hey, this is my training data. And then my testing data will probably be this one. The one thing you want to make sure when choosing these is that you want to, one, use the same data when splitting, right? But just make sure that both of the subsets of data is representative of the data as a whole. Do not pick a test set with different characteristics in the training set. So Also make sure your test set is large enough to yield statistically meaningful results. So if you take a statistic class, you'll learn more about this. I'm just not going to go over it today. It's just not that important. It's important, but like, you know, there's more important things to go over. Anyways, overfitting. I talked about this a lot. This is something you want to avoid, right? And you could have a machine model with 99% accuracy, but that could just mean that you overfitted when you were training your data. So you probably trained it so much that your data was fit to every single data point, but not representative as a whole. So when you train with new data, it actually is not going to yield good accuracy or good results. So basically, overfitting is the model doesn't generalize well between the training data and the unseen data. And some of the ways to avoid overfitting is cross-validation. You want to train with more data. You do early stopping and regularization. So cross-validation is a technique for evaluating machine learning models by training several ML models on subsets of the available input data. So see that we built like a couple set of subsets out of our main set of data. And you want to evaluate them on the complementary subset of data. Increasing the size of your data, however, should reduce spurious correlations, and they should improve the performance of your learner. No matter what, usually, as long as you're not giving it a noise as data, increasing the size of your data set always works. But it might not always be the option because it might not be cost effective. As for early stopping, if you see the graph up there right next to the meme, you want to, if you're compiling or running your model, you might just want to stop early. You want to see where, you might want to record your error, right? And the place where the error is least, you just want to stop there. Because if you keep feeding it more data, or if you keep running the program, it might start overfitting to the data. As for regularization, having regularization keeps the weights of your model at a manageable size, and we just went over this previously. All right, so this is another example of overfitting and it being just right. If you train your model too much or you don't have a good representative data set, you'll find that most of the line, or like the imaginary line that your model draws, is fit to every single point instead of being representative as a curve or a best fit curve. And you usually want a curve on the right-hand side. But yeah, it's just another example. So perceptrons, this is what we're going to code today. They are perceptrons take inputs of numeric value, and it assigns that data, it does some math and assigns that data a discrete label of 0 or 1. So it's more of like a binary output. You take maybe like 8 features and it turns out like 2 answers, yes or no, perhaps. We have a continuous output function to define these discrete values of the output, and we'll see more of that when we code the neural network. So here's actually what an actual neural network might look like. We'll have a set of inputs right there with a bias, and if you know anything about your data beforehand, which would be great, you can actually set a bias value so that your model works better. As for the weights, it can be considered as the parameter within a neural network that transforms the input data within the network's hidden layers. We initialize our weight near 0 when we start, and you'll see why. But we'll see this when we code a neural network. Our perceptron assigns 1 if the weight times the input, which is W times X in the summation section. If it's greater than 0, it'll be assigned 1. And it'll be 0 otherwise. And this will be our activation function that we have previously gone over. But yeah, at the very end, your output will be just a 0 or a 1. So when you train your perceptron, here's some pseudocode. I actually took this straight from my professor's notes from Grad AI. You want to initialize your weight vector, usually near 0 as an initial guess. Recall X as a vector of inputs and Y as the output. And underline X just means that it is a vector or like an array of numbers. And then given some data, if a linear separator exists, these set of instructions will discover it. So once you've initialized your weight vector, you're going to choose some data point, which is going to be like some set of vectors and an output value, your y, 0 or 1, in the data set. And from that data set, you're going to update parameters based on how poorly the model performed on that specific data point. So this is where you would have maybe something like a regularization function. And then you'll just rinse and repeat. So let's actually code a perceptron from scratch using NumPy. If you guys, I should probably pull this down. If you guys go on tinyurl.com/Hacker Hour, there will be code called templatecode.py. If you want to follow along, that's great. Otherwise, just watch me code. Let's see. Codetogether.py should be the name of the file. I kind of had some stuff pre-filled for you guys just so like we don't have to worry about writing the class definition or the function headers. More so we can just focus on how to learn how to train the data, how to multiply the vectors using NumPy, and I guess, yeah, the main function will call all of the functions for you, and it's hopefully well commented so that it's easier to like understand. It's step by step. I'll give you like 5 minutes to set up. Let me know when you guys are ready, by the way. Oh, is it too small? My bad. It was good. Are you guys all ready? Or is there anyone who's not ready? Raise their hand. Yeah, of course. What's up?
Give them time to like ask questions if they have any, just like as you go through it.
Oh yeah.
I'm just reminding you.
You good? All right, cool. So let's start with the definition of our perceptron. We want to initialize those weights, that vector of weights, as 0 for an initial guess, right? Or near 0 at least, right? So let's just enumerate that. Weights. If weight is none, right? We're going to actually do self-dot weights. Whoops, self-dot is equal to NumPy. By the way, I just imported NumPy as NP just to be a little bit quicker. But yeah, NP dot random input length. And input length is already defined as the header of the function. Times 0.01. This could be 0.01, 0.1. If you actually want to just mess with the numbers here, that's the whole part of learning. You'll see why some numbers work better than others. You don't want to put 500. It's awful. But you'll see why. We can mess with that later, though. So then, for a perceptron, a learning rate is not actually needed, but just for the sake of, I guess, documentation, or like if you were to build another neural network like linear regression, you would have like self-dot learning rate is equal to 1. And it's just going to be 1 times whatever you were working with. So since it's a perceptron, we don't want it to affect anything, so we just set it to 1. So that's just how we're going to actually initialize our work. If you really cared, you could have a generations, which is the number of times you want to train your data. But for now, we're just going to skip that because our data set is so small to begin with. It'll overfit immediately. Oopsies. So when we update, right, we want to go through actually all of the input data. And we're given the input data as of in the header, so we're just going to do for ion range length of input data. This is all coded in Python, by the way. I probably should have specified that, but it's all in GitHub. Anyways, once you have actually made the for loop, you want to actually access the weights, inputs, and labels. So you're going to set x equal to self.weights. You're going to have w, wait, whoopsies, this is w, right? But x is going to be input data at I, 0. And let me just quickly go over what the data looks like. This could be completely different based on how you're taking in data or what kind of data you're looking at. But for us, we just have a bunch of 1s and 0s. And actually, while I'm at it, I'm going to describe what some of this data looks like. So, can everyone see the board from here? Is it let me know if it's not easy to see. I'll move. We have 2 classifiers, class A and then class B, right? And it's going to be a 5x5 box, which will convert to a 1-dimensional array in the code. It's already converted, but this is for our visual understanding. We can think of the 1s as it's colored in or something similar to that sort, right? So I'm going to say classifier A looks something like this. And classifier B, on the other hand, look something more like maybe this. I know these are just like 2 pieces of data, so it's not easy to tell right off the bat. But what do you guys think the pattern is? What defines class B? What defines class A? Like just looking as humans, not as a machine. Does anyone know? Yeah, what is it?
Looks like there's like a triangular block set near the bottom of
So you're saying like, you want to draw it on the board?
It looks like there's sort of something like this for class A and then like something around here for class B.
Yeah, so you're pretty close, right? When we're looking at it, right, we want to say, well, how am I going to generalize these two? Where should most of the data sets fall in one side versus the other side, right? So if we have a 5 by 5, right, we want to technically draw a line, right? But it can't be drawn perfectly, right? Because we only have a 5 by 5 matrix. If it was an even one, it would be slightly easier. But yeah, so we want our model to basically draw this line. But how are you actually going to make a machine do that? Well, you build a perceptron. So let's go back to here. We have class A defined. The ones are basically the colored in lines. And then the zeros are basically the non-colored lines. You can mess with your own data for this if you want to put in different inputs or ones in different places. Your input data is going to be actually your training data. So make sure that it can still correctly classify the line, or you can draw them horizontally or vertically where most of like the data falls or where most of the ones fall. Your test set is going to be mystery, right? Like you don't know what the answer is going to be. Those are like the ones that don't have labels. So does anyone have questions at this point? Cool. So let's go back to this. Taking the input data at I sub 0 is just saying, hey, I'm looking at it here, and I'm going to be looking at these arrays specifically. Only. And looking at this actually gives us the output, which is your Y value. So let's just fill that in real quick. Y is going to be equal to input data at I1. And now you want to call your activation function. And we'll go over coding that in a second, so I'm just going to call the activation function real quick. Let's see. We want to say our guess is going to be self.guess on the input set. And do regularization next, which is going to be our loss equals the guess minus Y. And the guess minus Y means we already have our output, right? And we want to know what our guess is. Our guess is going to either be 0 or 1. If the loss is nothing, then we did good, right? But if there is some value of loss, we need to adjust. So we're going to update the weights based on that. So you're going to say self.weights is going to equal to numpy.subtract from the weights. You're going to subtract that with the learning rate, which in this case is just 1. Recall in a perceptron, the learning rate is only 1 because you don't need it. Self.learning rate is multiplied by np.multiply. And this is going to just multiply the two vectors, the loss vector, and with it's going to multiply loss with the vector x, which is your set of inputs. Sorry. So now we've basically done the whole update function, where it's just going to call the activation function, do regularization, and update the weights based off of the regularization. Now you're going to actually train your data, and you're going to just choose some data point, which is an x vector, right, from the pseudocode in the slides. Right here, you're going to choose some data point x, y in the data set and update those parameters. So this is where you'll also call update. So let's just start with this train for underscore in range self numgens. In this case, our number of generations will just be 1. You can make it more if you want to. But this is supposed to just indicate when you're working with larger models, you want to put a larger n value or a larger range. You're going to actually update the parameters based on how poorly the model performs on the specific data set. So you're going to do self.update input data. And actually, to make this a better programming practice, we should just have numgens, self.numgens. And we'll just quickly define it here as well. So does that make sense so far? The whole point of train is just to update the model n many times. In this case, we're making numgens equal to 1, so we're only updating it 1 time. So let's go into what the activation function actually is. It's actually pretty easy, right? You just want to make, if your weight times your input is greater than 0, it's 1. Otherwise, it's 0. AI is just like a bunch of fancy if-else statements, really. If you've seen memes about that, that's your meme. Anyways, so yeah, if NP, and we're going to take the dot product of those two. If you've ever taken linear algebra, good, you know what this is. If you're a freshman, I'm really sorry, but like it's the only way I could like present it. But you just multiply 2 arrays, and it's just multiplying the first index of the value by the first index of the other value of the array, all the way to the nth value. But yeah, so np dot, let's see, self.weights with x. And if this is greater than or equal to 0, I guess in my case, you're going to return 1. Otherwise, you're just going to return 0. And this should basically be your entire neural network. You can print the weights if you want to see what's actually happening behind the scenes. Just for now, I'm not going to, but if you want, the code is on the GitHub, so you can mess around with it as much as you want. Hopefully, this will compile. Hopefully. But yeah. So let's try to actually compile it. Let me just quickly go over what the main function does, which is basically it's going to instantiate an instance of the Perceptron class. So you'll just say P equals Perceptron 25. The reason why I put 25 in there was because based on our data set of 5 by 5, it's going to be 25 arrays of length 25. This will just do some work behind the scenes for us. If you just look at the code base, we can actually just look at it right now. Input length is what we're actually inputting, which is going to be that 25. And you're going to take random values and just multiply by 0.1. So let's see. Yeah, so once you've done that, once you've instantiated your data, you're actually going to train the data based on the training data that we had, which was up here, the data. And then you're gonna now go through each specific item in mystery, which is probably like 5 items, and it's going to say if it's class A or class B. So let's hopefully compile this, and hopefully it'll run. Python, let's see, code together, .py. Awesome. Love it. I screwed around with it, and I don't know how to change it back, so it's super annoying. If anyone knows how to fix that, please let me know. I'll love you forever. Otherwise, I don't know how I did it. Oh, I think the spacing is like off here. Subtract. Oh, I spelled subtract wrong. All right, cool. So it took all of the inputs and actually outputted if it was class B or class A. And you'll see that it's BA, right? So let's actually look at our mystery data. Did our algorithm actually learn what the answer was? Did he do what Carolus did and like imaginarily draw a line between a diagonal from the 0th index to the very last set of indexes? We'll see. I'm just going to zoom in a little bit more just so the data is a little more clear. So this was our first one, right? And let me just rewrite what the output was from the terminal. It was, I gotta stop doing that. It was B, A, B, A, B, right? So this looks like it's actually on the side of B, right? This is close. This has more data that is closer to the top right side than it is to the bottom left side. Does everyone agree with that? So we'll see that. Oh, okay. What about this one? We have some here, which is kind of weird. But what about the two data sets here? Probably based on these two, our algorithm decided, hey, this is more closer to the A side than it is to the B side. Let's think about this one. This has more, if you count, there's more on the B side than there is on the A side. And we count these as the diagonals, right? So there's a couple more here than there is here. So our classifier will define it as class B. For our fourth one, it's more clearly near the A side. There's one more data set or data point that's closer to A. And for the last one, it's actually all over the place, right? So why was it actually B? Let's see if we run this a couple more times. Will we get B again? Okay, so we get B again, and B again. So I could probably do this for like a day and still get B. And does anyone know why that might be the reason? Auleen? Do you know why the last mystery data set might be the reason that we get B all the time? Overfitting. So it's overfitting. For some reason, our model will tend to classify the outputs more on the times of B than the times of A. So if we drew the last data set, it would have been an array with one coloring here, one coloring here, one coloring here, one coloring here, and one coloring here. We actually want our algorithm to be unsure about this piece of data, right? Because it doesn't really make sense if it was A all the time, and it doesn't really make sense if it was B all the time. We wanted to probabilistically determine this. You'll learn this more if you take an AI class, but yeah, this is a result of overfitting. And one of the main reasons why our current program overfitted was because we only had 5 pieces of data that classify as A and 5 pieces of data that classified as B. So when we trained that one time on the 10 pieces of data, it's not really that much data to look at. So that's one important thing to take into consideration. If you guys decide to take another class or learn about linear regression and apply a linear regression algorithm to this model or to this data, right? Yours might just say A or B half the time based on how you train your data, or it could also mean that you'll always get A one time. It's all based on your algorithm, and you can also change certain things. If I decided to let me make this smaller. If I decided to make this actually 5, right? This is a rather large number. I'm just going to open a new terminal. If we run this, it's always going to now classify as class B. So maybe not actually initializing it near 0 makes sense, right? Let's do if it was 0.001, right? This is a really small number. Let's save and run it. It's also going to be BA, right? So you can mess around with some of the things, right? You can also mess around with the learning rate, right? But since we're training once, it won't really affect it that much, though I don't know for sure. You can change the number of generations, the number of times you're training your data. And it's a whole experience of messing around with it. A lot of researchers just do research on what's the best learning rate for an algorithm or for this specific problem, right? Or what's the best, when is the best time to stop early to avoid overfitting your data, right? But yeah, I really encourage you guys to consider AI as classes to take in the future if you haven't already. I've only just skimmed the surface, and I'm pretty sure the first time I learned this, it all went over my head. So if you guys understood this, or understood 10% of it, you probably know more than me when I first started. So I really suggest that you guys take what you learn, go learn TensorFlow, do what you can, email me if you have questions. But yeah, let's go back to, how do I present from current slide? All right, so that was just some introduction to coding from scratch. Most of the time you'll be working with stuff like TensorFlow and Keras if you use Python. But yeah, so thanks for coming for the pizza and for learning about neural networks. Email me for questions.